So for net ionic equations, now that you know about solubility, like you get the general little concept of solubility and how it works, what I want to show you is 5 steps for how one goes about predicting the products of net ionic equations specifically. Now, the first step is what you're already good at doing. You just simply predict the products, predict and balance reactions. So what I mean by that is, like the equation that we already did in the notes earlier, you've got zinc NO32 plus NH4. You're going to have 2 there plus ZnS. I wrote the 2 there, or the S there. We'll talk about why there's an S there in a minute. And then you got your 2 there. Okay. Now, that's step 1. That's like part 1. You can do that. Part 2 now, this is where it'll be new. You identify... Now, well, you know it's a double displacement reaction. We're not doing that part. I guess it's assumed that that's already done. So instead, you identify the phases / solubility of compounds. Now, I already did that for zinc sulfide. I already said it's an S. But if you would like to confirm, you can look it up and you can find zinc. And you can go over to sulfide and you see it as a solid. Now, if you do this for the rest of them, like look up the rest. You've got zinc nitrate. That's aqueous. So you're going to make a little note of that. It's AQ. If you look up the rest of these, you're going to find that they are all aqueous in solution. Okay? So that part's not bad. The next part is the step that's kind of long and annoying. So you're going to write the total Ionic equation. In simple terms, that means you're going to split everything that is aqueous. So you're going to split everything that's aqueous from the equation. Just like I was showing you for solubility. Because if it's soluble, that means it will dissociate in solution, which is a fancy term for dissolve. So, let's look at zinc nitrate. Is it aqueous? Yes. Yes, it is aqueous. It is aqueous, yes. So what you need to do then, you need to say, okay, we've got zinc, we got nitrate, it's aqueous. Here's what you do. You take your zinc, and you're going to want to start at the far left, and you're going to use up the whole line. So, right small. So there's zinc, it's a +2 ion, it's aqueous. Plus nitrate now. So what you're going to do, you're going to literally write the ionic form of everything in solution that is aqueous. So then nitrate, how many nitrates do we have?
2.
2. So you put a 2 in front. This 2 gets moved to the beginning, and you end up with 2 NO3s, each with a -1 charge. They're both aqueous. You keep going. You have 2 ammoniums, NH4 +1. They're aqueous. Again. Now, sulfur, you got -2. You have 1 of those. That's aqueous. Draw your arrow. Now, zinc sulfide, is that aqueous?
No.
No, so what you do, you just write zinc sulfide is a solid, just like that. And you leave it alone. You don't touch it. There's no ionic charges. It doesn't dissociate. It's just left by itself. Then you just keep going. You end up with 2 NH4s +1 aqueous plus 2 NO3s -1 aqueous. Remember that 2, the coefficient 2 applies to both things that it's in front of.
Wait, so then why didn't you just
What do you mean?
like why didn't
Because when you put them in a solution, you end up with 2 ammoniums and 2 nitrates in solution.
Oh.
So that's why. Because like they don't combine. When they're put in there, they break apart. So that's the long one. That's the pain in the butt one. Now step 4. For step 4, basically, it says cancel out spectator ions. Now, what is a spectator ion? Well, that's a good question. I have a definition for you to write down. Whatever. The definition is, so make a little note here so you know it. They are ions in solution that do not react. In simple terms, though, they are the same on both sides. So what does that mean for you? Well, take that paper and the paper over there that looks like homework. See you. So, spectator ions are ions in solution that do not react. They're the same on both sides. So what I mean by that is this. Slam the door louder, Nicole. That was funny. Alright. Now, the way this works, you're going to cancel out stuff that's the same on both sides. So, zinc plus 2. Do you have zinc plus 2 on both sides? No, you do not. You have zinc over here, and you do have zinc over here, but this is in its ionic form in an aqueous solution. This is zinc sulfide in a solid. They are not the same. But look at NO3. You have 2 of them, 2 of them. Those cancel out. If they're exactly the same, you just cancel them out. And then like NH4, you got 2 of them, it's plus 1. They're both right there, you can cancel those out. And then obviously again, S negative 2, you can't cancel that out because again, it's zinc sulfide in a solid on the other side. So the 5th step, the final step, is simply write the net ionic equation. So what I mean by that is simply take everything that you did not cross off and write it down here. So zinc plus 2, aqueous plus sulfur negative 2, aqueous, and then zinc sulfide solid. And that's your net ionic equation. So the end result is this. That's it. That's your goal.
So this is just for double.
So this is only for double displacement reactions that are occurring in solution. Well, yeah, there's no way to do this for single or combustion or synthesis or decomposition. It's not possible. Now, the whole idea is that what you see here, the only thing that actually happens in the reaction is when zinc ions contact sulfur ions, they make this compound. What you can see here is that your nitrate and your ammonium ions, they don't do anything. Because when nitrate and ammonium come into contact, they do form a compound. They do form ammonium nitrate. But in doing so, it's soluble, so they immediately dissolve, so in reality, nothing happens. So that's why they're called spectator ions. Now, I do want to show you one other problem before we do any work on the homework. Because it's actually kind of nice and it makes things a little easier sometimes. So let's also do this one. But we're going to skip a few steps to save some time. So NaCl plus K, NO3, Na, NO3 plus KCl. So I've predicted the products already for you. It also has no need to balance because everything has a charge of plus 1. It's just 1 to 1 to 1 to 1. This is aqueous That's aqueous. That's aqueous. How do I know this? I've done this problem 5 hours in a row. Plus, these are all soluble things. Anything with like nitrate is always soluble. Basically, anything with like alkaline metals is always soluble, almost too, like potassium and sodium. Same with chlorides. Anyway, so you look here; they're all aqueous, right? So here's what you would do. So that was like step 1 and 2 right there. Now step 3, where you are going to write out the total ionic equation. I'm just doing this to like show you something, to make something very easy for you to understand. So you start writing, you separate everything out. So that's aqueous, chlorine's -1, that's aqueous, plus potassium, +1, aqueous. So you keep going. All right, that was the fastest I think I've written it out yet. So, you write that all out. You have your full total ionic equation written out. So you write out your total ionic equation. Now, step 4, cancel out spectator ions. Here's what I'm trying to show you. Now, if you look at this, your spectator ions, again, they're the same on both sides. So if you look, sodium +1. Is it also over here, sodium +1?
Yeah.
Yes, it is. What about chlorine? -1, -1. How about potassium?
Yes, on both sides.
And then nitrate, both sides again.
So there's nothing.
So, yes, we just crossed everything off.
So nothing.
So, for step 5, where it's like write the net ionic equation, you would just indicate no reaction takes place. NR, no reaction. Well, the point is, I show you this so that when you see 4 compounds like this in a double displacement net ionic thing, if all 4 are aqueous, you just write. You don't even need to do this. You can just be like, no reaction takes place. So you skip all this and you just write NR, because everything cancels out. There is no reaction. So like in single displacement, how when you're using the activity series, you know, when you're using your activity series, if something is higher than the other one, you know, it will or will not happen. In this one, if they're all aqueous, nothing happens. Yes?
Does the same thing happen if they're all solid?
If they're all solid, then actually, yeah, no reaction would occur either, truthfully. And you wouldn't, and what you would end up having, you would have 2 solid reactants, and then there would just be no products, truthfully. Because there, yeah. So, that's interesting. Yes?
So for the one that we did in the beginning with the example we did, so did you like look on this chart for ammonium and nitrate and you found that it was aqueous?
Yes.
So that's why you had to split them up
Yes.
into, okay.
Yeah, you look on the chart, you find out if it's aqueous, that's how you know.
Alright.
She's got
So,
to ask her question.
what?
Oh, go ahead.
Okay, wait.
Alright, so
Should I hire my volume for voice? Okay.
Goodbye,
So.
volume.
I'm going to cut this part out now. Go
No,
ahead.
no, don't. Can I go up?
Cut it out.
No. Okay, I swear. Alright. So you see the part that's so you know how there's a solid on the other side? Do I have to go out and write out everything? Or could I just keep the solid and then the 2 things that make up the solid in the beginning? You understand what I mean?
Oh, good.
So can I just skip over that whole step 3?
she thought about
Really?
that the whole day.
Once you get it, yeah, that's fine. Unless I specifically on a thing say you have to show me step 3. Like on the homework, you have to show it to prove you get it. But after that, yeah, I know what you're saying. Yeah, that's
But
fine.
is that why the test is so long? Is because you have to do all of it?
Yeah, it's like, because in a lot of cases, it's not so obvious.
Okay.
I know what you're thinking, but it's not always that obvious.
Alright, got you.
All right, so let us do number 1 together. What, you got a question? What? What? Just ask.
No reaction.
No, there's a reaction for A.
Oh, I did wrong.
All right, so.
Labels on the staff.
Yeah, so here's the deal. Step 1 is going to be balancing and predicting. So I'm going to write it a little bigger here. Now, to predict this, remember, you're going to switch your 2 positive charges. You're going to trade their places. In a double displacement reaction, they're going to trade places. So you're going to end up with LiF plus Al, then in parentheses, NO3, 3. Now let me explain why that is.
So because Al is 3.
So yeah, so the reason it is you've got Al is plus 3, NO3 is negative 1. So when you crisscross your charges, you end up with Al1, then you have NO3 in parentheses with the 3 down there. Okay? Now, the next step
Balance.
is to balance it. Now, if you want to balance this, let's do that quickly. You've got 3 NO3s over here. You got 3 there. Let's put a 3 in front of that. Then that gives you 3 LIs. Put a 3 there. You have 3 LIs, 3 Fs, everything's balanced. All right. So, step 2. Step 2 now, identify the phases. So if you look up everything on your chart, you look up aluminum fluoride. That's a solid. Then everything else, once you look it up, will be aqueous. Everything else is aqueous. Now, once you do this, you then got to go to step 3, which is the total ionic equation. So, I'm going to, again, move it down here. I want to write with as much space as possible. Now, AlF3, that's a solid. So when I write that, do I split it up at all?
No.
No. Good job. You keep it together, you don't split it apart. You keep it together. No ionic charges or anything. You just write a plus. However, lithium nitrate, does that get split up?
Yes.
Yes, it does, because you've got lithium, you've got nitrate, it's aqueous. So you're going to split it up. You've got 3 lithiums. That's plus 1. They're aqueous. Plus 3 NO3s, negative 1, aqueous. Okay? You draw your arrow. Same concept over here. You've got 3 lithiums. Each one is plus 1. Aqueous plus 3 Fs, negative 1, aqueous. Pardon? Oh, yeah, I just forgot it. Sorry. Thank you. So you do that. Then you keep going. You've got aluminum. You've only got 1 aluminum, though. It's Al3. It's aqueous. Plus 3 NO3, negative 1, aqueous. So, all right, so you write all that out.
So I crisscross.
No crisscrossing.
Are you canceling?
Now you cancel out. So, first, are there any questions on that step 3 where anything came from at all?
No.
Okay. Now, to cancel everything out, what you will do. You're going to say, do we have 3 Al or AlF3 on both sides? No. Do we have 3 lithiums on both sides?
Yeah.
Yes, you do. So you're going to cancel those out. You have 3 nitrates on both sides. But then F3 or 3 Fs and Al, those all stay. So the only difference with this problem is that it's backwards. So the 5th step now is actually write out the answer. So the result here is that it's kind of backwards in that your problem now, you have the solid on the left side, and then you have your... Who's that?
Alright.
Oh, okay. So you do that, you end up with your final result, which in this case looks like it's a simple decomposition reaction. Now, are there questions on that? There's got to be questions.
Nope.
No, that was actually pretty easy. That you explained.
All of it is.
Not really.
Great. So, we're going to talk about double displacement reactions and net ionic equations. Now, if you notice, in looking at any of the equations from the PowerPoints, they're both aqueous. Both of the reactants are aqueous. Now, what that means for us, since they're both aqueous, That means double displacement reactions, for the most part, take place in solution. Now, to tell you what the heck solution means, let me show you. So, when we say something is aqueous, what we are saying is that something is dissolved in water. So let's imagine we have our water with our nice blue water in a beaker or something. Actually, before that, let me give you the definition of solubility really quick. So you should write everything, by the way. So, solubility. It's simply, really easy definition. The ability of a substance to dissolve, we're going to say in water only. Dissolve in water. Specifically water. So, some things dissolve in water, other things do not dissolve in water. It depends entirely on stuff. So there's this whole complex set of solubility rules, which you don't have to memorize yet. You have to memorize those in AP Chemistry, not here. And they're really not that complicated either. But let me give you an example. A substance that is soluble in water, NaCl, table salt. Salt dissolves in water, right?
Yes.
Yes, it does. Thank you. Yes, okay, your voice is on the video now. Congratulations. And when sodium chloride dissolves in water, here's how this is going to work. Now, you've poured salt into a beaker or whatever. You know salt water exists. What occurs? When you put it into water, it actually breaks apart. The ionic bond that holds NaCl together breaks apart, and you end up with a sodium ion and a chlorine ion. Okay, and they're separated like that. Now, in reality, there's a whole bunch of them just floating around in solution. I mean, there's more than you can imagine floating in any solution. And what that means, you have a bunch of sodium ions and a bunch of chlorine ions. Again, they're ions. When they break apart, they become their ionic form. So that's like really basic, simple solubility. Now, as I said, certain things can be soluble and other things are not. So, to account for that in this class specifically, we have this big solubility chart. Now, the chart is a little weird, in my opinion, but since we don't have a book, this is what we do. I figured I'd just give it to you. The chart, the way it works, it says S for solid and AQ for aqueous. Even though it's a measure of solubility, it specifically is going to say the S doesn't mean soluble. The S means solid. The AQ means aqueous. Okay? So let's do an example of something. Let's say you have calcium chloride. That's the answer to the warm-up question. Calcium chloride. Is that soluble or not? Is that solid or aqueous? So, you look up calcium, you look up chloride. It's aqueous. Or aqueous, as that one girl in third hour says. Aqueous.
Sounds like a type of
She's got the highest grade in the class, so I let her slide on it. Now, calcium chloride would be aqueous. Now, what that means to you, when you would want, so let's say that means in solution, this would be put in solution. What that means is that when it actually dissolves, here's how it breaks down. It breaks down to Ca plus 2, and then how many chlorines do I have here?
2.
2 chlorines. So it's going to break down into 2 chlorines, each with a -1 charge. Okay? You actually take this subscript and you write it as a coefficient out front when you are talking about something in a solution. Okay?
Yeah.
Okay.